Okay, for this screencast, we're going to go over some simple linear algebra techniques. Linear algebra can be offered as its own course, but we're just going to show you how to do the some MATLAB stuff. So say I want to solve the system of equations x plus y equals 2 and y minus x equals 4. So how would I solve this? Well, typically you just do substitution. So you say y equals 2 minus x. And then you say, okay, that means that 2 minus x equals 4. You substitute it into the other equation below. And then you get 2 minus 2x equals 4. And then 1 minus x equals 2. And then obviously x equals -1. Okay? Then you plug that back into y, so you get y equals 2 minus minus 1, which equals 3. And then you're done, right? So you could also graph this, and you could say, all right, I'm going to vary x from -4, 0.1 to 4. And you could actually rewrite both of these equations into two different forms. So you could translate this to y equals 2 minus x, and you could translate this to y equals 4 plus x. And then you could actually have y1 equals 2 minus x, and you could have y2 equals 4 plus x. And then we can make a figure, and we can plot x comma y1. We're going to do it in red. And we can plot x comma y2, and we can do that in blue. And if I plot that, oh, and I need to throw a hold on. What you'll notice is that they cross right at -1, 3. If I take the solution and I plot -1 comma 3, and I plot a black square with a marker size of say 4, and I plot that, what you'll notice is that the solution -1, 3 is right where those graphs intersect. So whenever you're solving a system of equations, you can visualize it graphically and see that where the lines intersect is where the solution is. Now we can also write this in matrix form. What we can do is we can say, okay, I'm going to take the coefficient, so I'm going to say 1 times x plus 1 times y, and then I'm going to rearrange this equation to be -1x plus 1 times y. And if I take these coefficients and I place them into a matrix, so a equals 1, 1, -1, 1, and then I make a vector b, which is 2, 4, b equals 2, 4, well then now I have a system of equations where a times, and then I'm going to call it v equals b, and v is what I'm looking for. So if I solve this, I will get v equals xy. So that's what I'm trying to solve for. Now there's a few different ways to do it. The first way is Gaussian Elimination. So in what's it called? In MATLAB, you use a function called RREF. Now if you have a homework assignment on this, you're not allowed to use RREF, but I'm just going to show you what the answer would be. So it'd be A, B, so you augment the matrix, with B, and when I run this, you see over here the RREF of AB is the identity matrix and then the answer, -1, 3. So that's what Gaussian elimination does. And in class we'll show you how to do RREF by hand so that you can write a computer code to do it yourself instead of using RREF. Now, let's investigate a different solution where, or a different system of equations where 2 times x plus 2 times y equals 1 and x plus y equals 1. Now if we write this in the same way and we say a equals 2, 2, 1, 1, b equals 1, 1, and we do RREF of a, b, notice here that, let me throw a clear CLC close all so we don't get confused. Notice here that the second time we ran the RREF, we got 1, 1, 0, 0, and then 0, 1. So we got 0 equals 1, which doesn't make sense at all. Now, in order to visualize what's happening, what we can do is we can translate these two functions into the form we had before. So this is y equals 1 minus 2 times x divided by 2. And then this equation here is y equals 1 minus x. So if we say again x equals, and I'm going to vary it from -4 to 4, and y1 is, 1 minus 2 times x over 2, y2 is 1 minus x, and then I do another figure, and I plot x comma y1 in red, and plot x comma y2 in blue, and I run that, and I forgot to do the hold on again. Notice here, these graphs don't intersect. So the reason why RREF gave you a 0 equals 1 and didn't return the correct solution was because the graphs are actually parallel. So they don't actually ever intersect. So a lot of times what RREF does, this is actually called naive Gaussian elimination, because it's naive in the sense that it doesn't check to see whether or not the matrix has an actual solution. It just turns the crank and spits out whatever it can. Now what's useful is to actually compute something called the determinant. So again, we're going to show how to do this in class, but if I run the determinant of A up here, you see that the determinant here is 2, which means it's non-zero. That means since it's 2, the solution exists. Now if I take the down here, if I take the determinant of A here, notice that I get a 0 determinant. So what is a determinant? Well, the other way to compute it is to actually say A of 1 comma 1 times A of 2 comma 2 minus A of 1 comma 2 times A of 2 comma 1. And notice here we get the same thing, 0, 0. So if you look at the matrix A, what it is 2 times 1 minus 2 times 1. For the other matrix up here, let me unconcatenate this guy. This matrix is 1 times 1, which is 1, minus -1 times 1. Negative minus a negative is a positive, so that's 1 plus 1 is 2. And that's why you get 2 there. So the moral of the story is, if your determinant is non-zero, it means the solution exists. If the determinant is 0, it means the lines are parallel and there is no solution. Now we can do this for a 3x3 as well. So let's do a 3 solution example. So I'm going to say I have A is 1, 1, 2, -1, 1, 3, 2, 4, 5, and B is 2, 3, 5. No, that's 2, 4, 5, and then the B is 2, 4, 5. So now my solution is still A times V equals B, but V equals X, Y, Z. Now if I do RREF of, first let's check the determinant. If I do determinant of A, I get that the determinant is -8, which means the solution exists. And then I'm going to do RREF of A, B. And it says it doesn't like, okay, because B needs to be a vertical. And here we go. So my answer is X is -3.75, Y is -0.125, and Z is 1.25. Now again, we can visualize this graphically by translating this into the form that we want. So I'm going to say that X varies from -2 to 2, Y goes from -2 to 2. In MATLAB, in order to plot two-dimensional surfaces, you have to do a mesh grid of X comma Y. And then what I'm going to do, and I'm actually just going to keep it XY just so I don't confuse everybody. And then now we have to translate this matrix into 3 equations. So I'm going to have Z1 is 2 minus X minus Y over 2. Then I'm going to have Z2 is 4 plus X minus Y over 3. And then Z3 is 5 minus 2 times X minus 4 times Y over 5. And how did I get those? Those are from the coefficients here. So 2 is this guy, minus X, which is here, minus Y, which is 1, and then divided by 2. And then the second row is, that should be the second row is 4, yes, 4, which is this guy, plus x, -1, minus y divided by 3. And then finally, 5 minus 2 times x minus 4 times y divided by 5. If you'd like, do it by hand so it sort of makes sense. And then now all we have to do is we just do mesh of x, y, z1, and I'm going to do something called face color I'm going to do it in red, and then I'm going to do edge color also in red, and then I'm going to copy this, and I'm going to do Z2, I'm going to do green, I'm going to do it again, I'm going to do Z3, and I'm going to do it in blue. And what we should see, and I forgot to hold on, I always forget to hold on, what we should see is 3 surfaces in 3 dimensions, and what we notice is they all intersect right here at this point right here. And that point, believe it or not, if we put our cursor there and grab it, it's almost, see, z is 1.2, 1.25, it's close, -0.1, -0.125, and then -0.375. If we plot 3, -0.375, -0.125, 1.25, and we plot a black square with a marker size of, say, 10, we notice that there is our black square right at our solution. So again, in 2 dimensions, you have 2 lines intersect. In 3 dimensions, you have 3 surfaces intersect. If you had a 4-dimensional matrices, you would essentially have 4 hyperplanes intersecting. And essentially what we can do is we can do the exact same example, except we can change the matrix A to be 1, 1, 2, -2, -2, -4, and everything else stays the same. And then if we look at our determinant, and let me do a clear CLC and a close all. If we look at our determinant is 0, and we see again RREF returns 0, 0, 1. And so if we change the Z2 plane to 4 plus 2 times x plus 2 times y divided by -4, and we plot this, what we notice is that that second plane dropped down and is now parallel to the red plane. So again, we have no intersection, our determinant is 0, our planes don't intersect, and RREF returns no solution. So all of these are linked. I'm going to pause here for sake of time, and then we will pick up on eigenvalue analysis.